This meeting is being recorded.
Okay. You can begin, Professor Sakallı.
Do you see my screen?
Yes.
Okay. So I can start, I think. Just a minute. Okay. First of all, I would like to thank to the organizers making this international conference possible. And it is going to be a traditional conference because this is the fourth one. And year by year, I am seeing that it goes much better conference. So thank you for these efforts to make these conferences available. And also special thanks to the local organizers, scientific committee members, and both the members of Kazar University and the Dunkl University. My talk title is Dunkl Black Hole with Phantom Global Monopoles. Over there, I will try to give some analysis about geodesics, thermodynamics, and shadow. This work is based on our recent paper published in EPJC with my dear colleagues, Professor Dr. Ahmet Albadawi and Professor Dr. Faizin Din Ahmet. Yeah, that was my thank you part to the organizer, but I already did it. But special thanks to Professor Behnam Purasan and the Shahin Mahmudov, who did a great work on the behalf of Dunkl University and the Kazar University. Thank you very much. And that is the outline of my talk. First, I will introduce what's the Dunkl black hole and how it came up. And then I will try to express my motivation why we consider this black hole and why we are adding a global monopole to the Dunkl black hole. And I will also introduce how we added the global monopole to the Dunkl modified Schwarzschild black hole. Then I will serve the geodesics motion for both null and the time-like geodesics. Then I will serve the thermal properties of the Dunkl black hole with global monopoles. Actually, our aim is to reveal the effect of global monopole on thermal features. Then I will also serve how the global monopoles affect the shadows of Dunkl black hole, and then I will draw my conclusion. Actually, our EPJC work was based on those two recent papers. One was made by Sadakani et al. In International Journal of Modern Physics A. And then Ashkur et al. They used this solution to get some constraints for Dunkl black holes using the data of M87 star and the CGRA star. As you know, CGRA star is the black hole at the center of our Milky Way galaxy. First, I would like to give a historical development of Dunkl black holes. In 1988, the Dunkl, actually he's a mathematician, he served differential difference operators with reflection groups. And he modified the differential operators by adding some reflection groups. So that was the onset of idea how someone can get spherically symmetric or spherical, the operators changed in spherical coordinates, which was made by Chayachian et al. In their physics letter B paper. Then the Chang and Hasanabi, they improved this technique of Chayachian et al. For a better design for spherical coordinates and their applications. And then that was the idea for Satakani et al. They use these differential difference operators of Dunkl to get modified Einstein equations, field equations. And then they derived the Dunkl modified Schwarzschild-like black hole. Then, as I mentioned, in J-Hab paper, of Askur et al., which is one of the recent papers, observational and simulatory paper for Dunkl black holes, for those two black holes, M87 star and the CGR A star. Then, with my colleagues, as I mentioned, we added global monopoles, and the more effective one is the phantom global monopole. That's why the title of the paper highlights the phantom global monopole. But actually, we used both ordinary global monopole and the phantom global monopole together. Yeah, and sorry, those 10 papers can be seen as the main or trend papers on Dunkl black hole from its starting point to today. So, what are the Dunkl operators, especially in spherical coordinates? As we know, we have operators in spherical coordinates as the partial derivative of r, theta, and phi. But the Dunkl deformed these operators by adding parity operator represented by capital Ri and the Dunkl deformation parameter alpha I. So that was the mathematical, how to say, approach at the beginning. But as I mentioned, the Chang et al., Chang and Hasanabi especially, they used this operator to show up them. We can modify the spherical coordinates, which find themselves more applications in physics. So that was the idea for Satakani et al. To use them to drive a black hole with those operators. But what are these Pareto operators? I mean, RIs. There are actually two types. If it is positive one, we have a symmetric reflection. If the Ri is negative one, we have anti-symmetric reflection. So when they are implemented in, I mean, the Dunkl operator in spherical coordinates, if they are implemented in Einstein field equations, the strength tensor takes the following two forms, as can be seen in equation 2 and 3 of Sadekani et al. Paper. And in their paper, which has also archive number 2302.1146, one can easily check. At the appendix, they gave all the modified Einstein field equations due to the Dunkl operator. And at the end of the day, by using some ansatz for tetrad fields and therefore its outcomes spin coefficients, they impose them into the Einstein field equations. Here A is our metric function actually, and we have other constants. But at the end of the day, they got a one master field equation. So all the Einstein equations with null torsion came up with one important equation to be solved, which is equation 11. And over there, they defined the new parameter C, and they call it Dunkl parameter. And this Dunkl parameter now includes the parity parameter R and deformation parameter alpha. So that summation of the combination of alpha and R, now they all merge in the parameter Xi, so which is now the equation 12. And at the end of the day, they got the solution. This solution includes Xi, and there are some constants, beta and the gamma, coming from the integration constants, and they show them these beta and gamma actually they have physical correspondences. The gamma is related with the mass, and the beta is related with the cosmological constant. And this cosmological constant, I mean the lambda, is connected to the cosmological constant capital lambda as minus 12 lambda square. Anyway, when someone kills the deformation, we recover Einstein anti-de Sitter solution, which is in 14. And at the end of the day, once tuning all the parameters to the physical parameters, including mass and cosmological constant, they obtained the first Dunkl modified Schwarzschild black hole. As you see, here we have the powers of R, and they are non-integer, and this makes the horizon structure different than the Schwarzschild one. And also we have parity-dependent behaviors through Xi parameter, which is the Dunkl parameter. And as I mentioned, it reduces to the Schwarzschild de Sitter or anti-de Sitter when we kill the Dunkl parameter. Then, the Ashkur et al., as I mentioned in their JHA paper, they applied embedding techniques to show up the effect of the Dunkl parameter on the black hole structure. And they show that the Dunkl parameter effectively changes not only the horizon. By the way, the horizon, event horizon now is represented by red ring at the bottom, and also asymptotically flat structure. So the Dunkl is actually affecting the shape of the black hole as well. But they continued to their analysis with shadow, and they show that the shadow radius of the black hole with Dunkl parameter increases, and they obtain the critical orbit. And one can see that meanwhile in their paper they are using zeta instead of the Xi, but here the zeta is also the Dunkl parameter. But later on, when we pass to our paper, we will shift again the Xi instead of the zeta. So they also found that the maximum instability happens at 1.18 of the Dunkl parameter. They also use some data coming from astrophysics for M87 CGRA from those two interferometers, KEGG and VLTI. And they also found the constraints on the Dunkl parameter. So, and also they found another constraint coming from the angular diameter constraint. And they show up that this Dunkl parameter astrophysically should be less than 1, and it shouldn't be a very big number. But this is the constraints coming from those two black holes. But maybe for other black holes, that constraint might change if we had a data. And they also continue to analyze the deflection angle. As you know, the first term for m over beta, and the third term is the ordinary or classical deflection angle for Schwarzschild black hole. But the second term includes a Dunkl parameter effect. So the Dunkl parameter is also affecting the light deflection angle, and they made some comments on them, and I will also mention. And they also computed the Lyapunov exponent, because Lyapunov exponent quantifies how sensitive photon trajectories are to initial conditions near the critical radius. And as we know, maximum instability decreases with increasing, they prove that the maximum instability decreases with the increasing Dunkl parameter zeta. Actually, we are adding extra term, and maybe we were expecting more chaos, but this is counterintuitive, because now the maximum instability decreases with the help of Dunkl parameter. So the Dunkl parameter helps the stability, actually, according to the intuitive beliefs, let's say, or contrary to the intuitive beliefs. The Dunkl parameter plays a role on stability. And the exponent is evaluated at the critical photon orbit radius RC, which itself depends on the Dunkl parameter. So Dunkl parameter also affecting the critical orbit. Then they continued their analysis for plasma medium, and over there they computed the deflection angle. Again, over there it was seen that the maximum instability decreases with increasing Dunkl parameter. Again, in the plasma medium, the Dunkl parameter plays a role to decrease the instability. And they serve some nice shadows and lensing rings figures in order to highlight the effect of Dunkl parameter. And they continued with some testable predictions based on these shadow modifications by the Dunkl parameter. And they claim that these Dunkl parameter can be testable by using the data coming from the Event Horizon Telescope. And only we have two data about two black holes, and these are also show that we should have constrained Dunkl parameter. So these are the main outcomes or findings of that JHAB paper. And then, we used two main resources of Chen and Sheriff et al. Chen and Jing and the Sheriff Iftikhar papers to add global monopole to the Dunkl black hole solution. Then after some straightforward computations for considering the action, we added global monopole and the phantom ordinary global monopole and the phantom global monopole to the Dunkl modified Schwarzschild black hole. In that action, how we distinguish whether we have ordinary global monopole or phantom global monopole. Actually, we have to check the kinetic energy theorem, which is near to the richest scalar. I mean, the second term is now defining the kinetic energy. When the zeta is a positive one, we will have ordinary global monopole, and when the zeta is negative one, we will have phantom global monopole. So here in our work, the zeta is not a Dunkl, instead of it's a global monopole parameter, and that psi I, these are triplet scalar fields coming from SO3 symmetry, and this is actually the source of monopole. We will have also the eta, and this eta comes from symmetry breaking scale. Actually, it's an energy scale of defect formation. And we have lambda, this is self-coupling constant. It controls stability and interaction of fields. And as I mentioned, we have zeta now, which is the coupling in kinetic energy term. And it distinguishes ordinary global monopole from phantom global monopole. As you know, if you look at the literature, ordinary global monopole models topological defects from early universe, and they have attractive effects. However, controversially, phantom global monopole represents exotic matter with repulsive effect. And this is relevant for modified gravity and lensing. Yeah, these are, I mentioned already. And then we also apply the embedding techniques that the works made in JHAB, because they were using only pure Dunkl black hole. And actually, the first three set is for pure Dunkl black hole because we don't have any global monopole. So first, we retrieved the embeddings of Akur et al. In their JHAB paper. But the last two shows the modification of black hole structures when we add ordinary global monopole, the second three set, and phantom global monopole. So now it's clear that when we compare all these three sets, if I have ordinary global monopole, my black hole event horizon, if you look at the bottom, the red ring getting enlarged, and also it affects the asymptotically flat structure. So and my black hole a little bit gets fatter. So why? Because ordinary global monopole has attractive property. That means my black hole, in quotation mark, it's too much. So it makes my black holes bigger. But if you go to the phantom global monopole, it has a repulsive property. So as you see, if you look at again the bottoms event horizons, which are represented by red rings, they get shrink. I mean, a smaller one, and also the throats of the black holes are much more smaller. So this is also the signaling why the phantom global monopoles should have repulsive property. So in the middle we have Dunkl black hole without a global monopole, but these global monopoles, depending on its ordinariness or phantomness, it affects our black hole structure. And what we expect from those three-dimensional visualizations, these effects should also change the geodesic structure, thermodynamic structure, and lensing and the shadow properties as well. So our idea was based on that. So what we found, because our new metric is at the top one, FFR, now we have scaling energy scale parameter eta, and near to have we have zeta, and zeta is now my global monopole, and Xi, which can be seen at the first and the third terms, it stands for Dunkl parameter. So for pure Dunkl, if I don't have any global monopole, what we observe, increasing Dunkl parameter widens throat. That means stronger gravity. A small or negative Dunkl parameter, we will have narrower throat. But with ordinary global monopole, which are the middle three figures, which we labeled them with D and F, with D to F, the EF, I mean. And over there, we selected the zeta as +1 to represent the ordinary global monopole. We saw that throat enlarge versus pure Dunkl. Therefore, ordinary global monopole adds more attraction and a more deeper, actually, black hole. And we have a wider throat for larger Dunkl parameter. But with phantom one, the throat reduced versus ordinary global monopole, and the PGM, I mean the phantom global monopole repulsion makes our black hole narrower, shallower, and altered asymptotics. So phantom global monopole has more, how to say, effect on the black hole structure or black hole geometry. And if we compare the both two, whenever I have OGM, we will have wider and deeper throats. Whenever we have PGM, we will have narrower and flatter throats. And asymptotic differences are important because asymptotically they also make effect on the black hole geometry. So that might be observable in lensing and shadows, and that is what we have in our mind. And also our event horizon modified because of eta and zeta, I mean energy scale parameter and the global monopole parameter, in addition to the Dunkl black hole parameter, Xi. Sorry. Yes. Then we passed to geodesics motion. We applied a method. These are classical actual calculations. We use the Lagrangian method in equilateral plane. I mean, we selected the theta pivot 2. Then we found conserved quantities, energy, and angular momentum. We obtained effective potential. Over there, we had epsilon, as you know, one represents I mean null when epsilon is 0. And when epsilon is -1, we will have particle trajectories, I mean time-like. We computed photon sphere by making the first derivative of the effective potential to 0. We got a condition and we obtained it. Photon sphere radius can be seen if you follow the arrow at the top at the right. And we also computed the impact parameter, which is nothing but the ratio of angular momentum to energy, conserved energy. And we also got them. And we also found force on photons. And what we obtained, we saw that larger Dunkl parameter and energy parameter, Lorentz breaking energy parameter, eta weaken gravitational attraction. However, PGM amplifies this effect more. Then we made some numerical and computational works to highlight these differences. And we made some comparison plottings. In the figure 4, we served a comparison to effective potential for null geodesics in different black holes. Actually, we consider 3 types of black holes. One is pure Schwarzschild. Then the other is Dunkl black hole with ordinary global monopole. And we will have black hole with Schwarzschild with ordinary global monopole. And as you see, for right and left, you can see the differences. And because left belongs to ordinary global monopole plots, right belongs to phantom global monopole plots. Especially when we look at the effective potential, if I have ordinary global monopole, the peak of the effective potential belongs to the Schwarzschild one. But in the phantom global monopole, the peak now, actually not the peak, the lowest point belongs to the maximum points, I mean, belongs to the Schwarzschild one. So you see, the ordinary global monopole and the PGM makes a great differences on the effective potentials. And similarly, when we check the force on photon particles, if I have ordinary global monopole, our force on the photon particles is less. But if I have phantom global monopole effect, with pure one, without Dunkl, we have highest force, but if I have Schwarzschild with phantom global monopole, we have highest force. But if I have Dunkl one, this time the Dunkl effect decreases the force on the photon particles even more than the Schwarzschild black hole with phantom global monopole. So these are all testable things, I think. If in the future we will have more advanced interferometers. And also we check the Lyapunov exponents to make the comparison. Again, ordinary global monopole and the phantom global monopole effects are clear. We all highlighted them in our paper. Then we pass to the trajectories. We obtain Keplerian-like trajectory equation. And then we put the ordinary global monopole and then phantom global monopole into action to see how the trajectories are changing. Actually, here we have 3 colors. The red solid one belongs to the ordinary Schwarzschild black hole. And the other colors are with global monopole. So these are all highlighted. And at the end of the day, we found those outcomes. Ordinary global monopole preserves bounded precessing orbits, but phantom global monopoles weakens confinement. PGM enhances orbital divergence. However, OGM shows relatively stable patterns. When we check the Dunkl parameter in both cases, larger Dunkl black hole parameter broadens trajectories, but divergence is stronger with phantom global monopole. If we have negative Dunkl parameter, this time it produces weaker binding in ordinary global monopole. However, in phantom global monopole, it adds further instability and asymmetry. So overall, PGM significantly reduces gravitational attraction. This is very clear in geodesic trajectories and affecting orbital stability and precision. So this exotic matter field, which is the phantom global monopole, actually it will reduce the gravitational attraction than expected, and it will affect orbital stability and precision. Then we continue with computations of Lyapunov exponent, and we saw that when the lambda is greater than 0, circular null orbits are unstable, and instability again is stronger when we take into consideration of phantom global monopole. And also we continue with angular velocity, which can be again measured, and it is seen that it is modified by Dunkl parameter, and it reduces to the Schwarzschild one as expected, but our calculations verify all them when the Dunkl parameter is 0. We obtain time-like effective potential. Again, when we have higher Dunkl parameter and global monopole with that energy scale, we will have weaker binding. So that means something can easily escape. And we also computed both energy and angular momentum. Sorry. And then we computed the precision frequency. Over there, phantom global monopole reduces the precision frequency compared to the ordinary global monopole one. We also computed the circular speed at large R. It is modified by Dunkl parameter. However, it is independent of global monopole. This is a very remarkable point. So this circular speed at large R, it is only a Dunkl parameter. I mean, it governs by the Dunkl parameter, not by the global monopole one. Again, when I kill the Dunkl parameter, we recovered the Schwarzschild circular speed, which is very well known under the square root m over r. And these are frequencies and our precision frequency and orbital over there, angular velocity. These are exact values of those quantities. I didn't want to give too much detail. I prefer to give the interpretations that we obtained after the computations that we did. So therefore, what is the key takeaways up to now? The Dunkl black hole parameter epsilon and the monopole parameter eta, because without eta we cannot say that we have global monopole. Reshape effective potentials, photon spheres and stability. Phantom global monopole enhances instability and weaken gravitational binding or attraction. Photon deflection decreases with larger Dunkl parameter and monopole parameter, suggesting weaker lensing. When we check the time-like geodesics, we saw that phantom global monopole requires higher energy and angular momentum, but reduces precision frequency. And circular speeds at galactic scales depend only on Dunkl parameter. So at galactic scales, actually, our global monopoles will not be effective for circular speeds. So the boss or the main governor will be Dunkl parameter, not the monopoles. Then we continue with thermal properties with ordinary global monopole and the phantom global monopole. we found the mass function. And so positivity requires this condition, inequality, 8 pi eta square in a bracket 1 plus psi should be less than 1. For phantom global monopole, positivity always satisfied. We also obtained the Hawking temperature, and we saw that Hawking temperature decreases with both global monopole and the Dunkl parameter. So these parameters fades the Hawking radiation. We will have a lower radiation with their existence. But it is much lower in phantom global monopole than the ordinary global monopole, implying much weaker thermal radiation if we have phantom global monopole. So thermal detection of phantom global monopole will be much more difficult comparing with the ordinary global monopole. We obtained the entropy, but again in the entropy we saw that it is independent of global monopole. Again, it will depend on Dunkl parameter like circular speeds. Our entropy doesn't depend on global monopole. It only varies with the Dunkl one. One can easily check that when I insert psi as 0, the power of RH will be 0, and denominator will be 1 plus 3, 4. So we get A over 4 in the absence of Dunkl parameter. But our entropy, as I said before, it doesn't depend on the global monopole. We also computed the specific heat. In the next slide, I will give their plots. But for the beginning, what I say, for phantom global monopole, specific heat capacity is always negative. That means we have always thermal instability. For ordinary global monopole, see changes sign, I mean the specific heat changes sign depending on Dunkl parameter psi. Especially it is stable if psi is larger than -3 or 4. Otherwise it is unstable. And we also found phase transition conditions and critical points. We saw that they are independent of RH. They are determined by the other physical parameters, Dunkl, energy scale parameter, and the global monopole parameter zeta. PGM lacks stable phase. OGM always allows stability windows. So these are the specific heat figures that I obtained. As you see, the only difference in the specific heats at that sign difference in the denominator. If I have PGM, I have +1. But if I have ordinary global monopole, I have only -1. The other terms are similar, but the effect is very remarkable. I mean, when I have PGM or OGM. Especially here, as you see, this graphic illustrates that the Dunkl black hole with PGM, the heat capacity is always negative, indicating that the system is thermally unstable. But in contrast, for OGM, the stability of the black hole is determined by the Dunkl parameter because we can have positive specific heat values. So for thermal properties, if we check the key takeaways, I can say that the Dunkl parameter psi modifies all thermodynamic quantities, enlarging entropy and affecting stability thresholds. For PGM, specific heat always negative. That means we have always unstable thermal conditions. But for OGM, we can have thermal stability depending on psi, because when I have positive heat capacity, especially for Dunkl parameter when it is greater than -3 or 4, we will have thermally stable black holes with global monopole. Hawking temperature is suppressed by Dunkl and that eta parameter, but with PGM giving much colder black holes. So phantom global monopoles will cool our black hole comparing with its without global monopole version or with ordinary global monopole version. So PGMs will cool the black holes as well. And what we have so phase transition points depend on not RH actually, it depends on the black hole parameters. Mainly these are Dunkl, eta, and zeta. And finally we checked the shadow properties. For this aim, we use the photon sphere and the shadow radius methods. We got the shadow radius, and we saw that it grows with Dunkl parameter for both types of global monopoles. It doesn't matter. We use ordinary or phantom one. The shadow radius all the time grows with global monopole, and this is actually very important. And especially the effect of energy scale parameter, we saw that the RS increases with OGM and decreases with PGM. But they are comparing with its naive version or without global monopole version, our shadow radius is always greater than its standard Dunkl black hole within Schwarzschild or within a gravity version, pure gravity version. We also computed the celestial coordinates, and we saw that for equatorial observers, x squared plus y squared satisfies RS squares, which yielding circular shadows. So all the shadows that we obtain are circular. And larger Dunkl parameter always enlarges shadow size. And RS positively correlated with Dunkl parameter. And when we look at the shadow size, OGM consistently larger than PGM at the same parameters. When we use the same parameters for shadow radius, and when we compare the ordinary global monopole with the phantom global monopole, we saw that OGM enlarges the shadow more than PGM. Yes, these are the things that the shadow figures that we obtained, and those outcomes that I served in the previous slide are actually coming from that figure. So again, if I check the key takeaways of the shadows of Dunkl black holes, Dunkl parameter Xi directly controls the shadow radius. So higher Xi, that means larger shadow. And symmetry breaking scale, eta asymmetrically expands shadows in OGM, contracts in PGM. OGM black holes produce systematically larger shadows than the PGM counterparts. Shadows remain circular, there is no distortion, but size strongly encodes our parameters Xi, eta, and zeta. But this is why this is very important, because it may provide observational window to distinguish ordinary global monopole from the phantom global monopole in astrophysical data. So actually maybe the last outcome that I'm serving now is the whole story of our paper. So if we have such global monopoles in the future, how we will distinguish them? Maybe this study, hopefully this study will shed a light on those observational data. So key features. We first introduce the Dunkl geometry by giving its historical background. Then we modify the Schwarzschild solution I mean, we showed how it is modified with the parameter Xi, which is the Dunkl parameter. Then we added two types of different global monopoles, and all our article were based on it. We use OGM and the PGM, and we started to make their or to show up their differences on different physics like thermo, shadow, and geodesics. And then we found that the Dunkl parameter Xi and the monopole parameter eta or zeta, like, without eta, global monopoles doesn't come. They reshape the photon spheres, and they impact parameters and orbital stability. We show that PGM enhances instability, larger Lyapunov exponent, and weakens gravitational attraction compared with the OGM, I mean ordinary global monopole. Then we did Hawking radiation entropy and heat capacity computations, and they all modified with both Dunkl and global monopoles. But in particular, we identified that phantom global monopole black holes are always thermodynamically unstable. However, ordinary global monopole ones can be. Then we show Dunkl parameter Xi enlarges entropy and shifts stability thresholds, suppressing Hawking radiation, but especially PGM makes the black holes much more cooler comparing with all the others. Then we derive analytical expression for shadow radius, showing positive correlation with Dunkl parameter. And also we prove that OGM tends to or leads to larger shadows than the PGM ones, although the both global monopoles create a larger shadow comparing with pure Dunkl black hole. But among them, the shadows of ordinary global monopoles should be much, much larger with comparing with PGM ones. So we concluded that Dunkl symmetry and phantom monopoles significantly modify geodesics, thermodynamics, and shadows, providing potential astrophysical signatures to distinguish them from classical black holes like Schwarzschild 1. So this is my talk.
Thank
Thank you very
you.
much.
Is that any question? Okay. I have some questions, but let me ask you later because
Sure.
we have less than an hour for the lunch and should come back to see in-person talks with the same link. Thank you all. We'll see you soon.
Okay, thank you very much. Sorry if I